Now we want to begin to look at applications of derivatives. First, we're going to look at the derivative as a rate of change. Remember, we discussed previously the instantaneous rate of change of f with respect to x at x sub 0 is the derivative f prime of x sub 0, provided that limit exists. When we want to find the instantaneous rate of change of a function, we will simply find the derivative. We no longer have to use the derivative rule here, the derivative definition, since we have learned rules for finding derivatives of functions. Here we have a circle, and the area of the circle is related to the diameter by the equation a equals pi over 4 d squared. How fast does the area change with respect to the diameter when the diameter is 10 meters? Now we're looking for how fast does the area change. So we're looking at the change of the area. So what we want to know is what is the change in the area with respect to the diameter. Okay, so we're looking at how fast does the area change with respect to the diameter. So we're going to be finding the derivative of a with respect to d. Now this is just a power rule. Pi over 4, of course, is a constant multiple. And then we have our 2d. When you take the derivative of d squared, that will be 2d. So the derivative of our area with respect to our diameter is pi d over 2. Now we will know how fast does the area change with respect to the diameter when the diameter is 10 meters. So what that tells us is we want to find dA dd when d is equal to 10. That means we are going to substitute 10 for d, and 2 goes into 2 one time and into 10 5 times. That will give us 5 pi. Now, as we look at this, we do need units to go with this. It's not just 5 pi. We're looking at the change in area with respect to diameter. So we have to think about what are the units for our area if we're dealing with meters, and what's the units for our diameter. Remember, area is always square units, so this will be squared meters, and the diameter is in meters. So the change, how fast does the area change with respect to the diameter when the diameter is 10 meters is 5 pi meters squared per meter. Now, one application we see a lot of when we're talking about rates of change is the concept of velocity. And when we deal with instantaneous velocity, that's just the derivative of your position function with respect to time. So if we know our position function, then we can find the velocity by taking its derivative. Now remember that velocity tells us how fast an object is moving and the direction of motion. Velocity can be positive or negative. Positive when we're moving in the positive direction, and negative when we're going backwards. Notice here we have graphs of our position function. In the left graph, s is increasing. It has a positive slope and it is moving forward. In the graph to the right, s is decreasing. It has a negative slope, so it is moving backwards. Remember, the slope at any point would be our velocity. So when the slope is positive, our velocity is positive. When our slope is negative, our velocity is negative. Now, closely related to velocity is speed. Speed is the absolute value of velocity. Remember that speed is never negative. So with velocity, we could have positive or negative values. Speed will always be positive. Now, here's an example of a velocity graph. This graph shows us the velocity of a particle that's moving along a coordinate line. And by looking at this, we can tell certain things about how our particle is moving. First, if you look at the parts that are highlighted in blue, the velocity is positive in both of those places. That means that we are moving forward in both of those places. Notice the part highlighted in pink. The velocity is negative in that area, which means we are moving backwards. And then if you look between 5 and 6, where the velocity is constant and not moving, then that's where it is standing still. Okay? Notice here that the velocity is increasing. That means it's speeding up. Here the velocity is constant, and then as the velocity is decreasing, that means it's slowing down. Here the velocity is 0. That means at this point we have stopped. Now, notice here we're going in the backwards direction, and we're speeding up, and we get to a greatest backward speed here, and then we start slowing back down towards 0. Between 5 and 6, the velocity is 0, so we're standing still in this interval. And then starting at 6, we're speeding up again. Our velocity is increasing. Now the acceleration is the derivative of the velocity with respect to time. So the acceleration is the change in your velocity. If we want to know the acceleration, we simply take the derivative of the velocity function. Remember, the velocity function is the derivative of the position function. The derivative of acceleration is called jerk. You can think of jerk as a sudden change in acceleration. You know, if you were riding down the road and your acceleration changes very quickly, that is what we mean by jerk. And it is the derivative of your acceleration function. Now let's look at an example that deals with our position function, velocity, acceleration, and the relationship between those. Here we see this figure. It shows the free fall of a heavy ball bearing released from rest at time t equals 0 seconds. And you can see as it falls, in the first second it does not fall as far as it does between seconds 1 and 2. And between seconds 1 and 2 do not fall, it doesn't fall as far as it did between seconds 2 and 3, because it is speeding up as it falls. Okay? We want to know how many meters does the ball fall in the first 2 seconds and what its velocity, speed, and acceleration are in the first 2 seconds. Okay? Now, just by looking, a rough estimate, it looks like that at 2 seconds it has fallen about 20 feet. Or 20 meters, sorry, 20 meters. It is not exactly 20 meters. The way that we can tell how far it has fallen is by using the metric free fall equation. The metric free fall equation, S of t, is 4.9 t squared. Okay, so if we want to know how far this ball has fallen in 2 seconds, we will find S of t, which means we will plug in, S of 2, which means we will plug in 2 for our t function. So that would be 4.9 times 4, which is 19.6. Now we are dealing here with position, and we're looking at how far it has traveled, so our units here will be meters. So we saw from the picture that it looked like it had traveled about 20 meters. It had actually traveled 19.6 meters during those first 2 seconds. Now we want to know the velocity and the speed of this ball bearing that's falling at 2 seconds. Now the velocity function is the derivative of our position function. So we go to our position function and take the derivative. Now the 2 becomes a coefficient, so we have 2 times 4.9 t, which is 9.8 t. So this formula will tell us the velocity at any given time. If I want to know the velocity at time 2, then I just plug in my 2, and that will give me 19.6, and we are dealing here with speed or velocity, so it's meters per second. Okay, so at time 2, we're now traveling at 19.6 meters per second. Now that is the same as the speed. If it had been negative, we would have taken its absolute value to find the speed, but the speed at time t equals 2 is also 19.6 meters per second. Since the velocity is positive, that means it's moving in a positive direction and not going backwards. Now we want to find the acceleration at that time, 2. Acceleration is the derivative of our velocity function. So if we take our velocity function, which is 9.8 t, take its derivative, it will be 9.8. And you'll notice it's a constant. So it has a constant acceleration. And our acceleration will be meters per second squared. So our position at time 2 is 19.6 meters. We have traveled our ball bearing has traveled 19.6 meters. Our velocity at time t equals 2 seconds is 19.6 meters per second. And the acceleration is 9.8 meters per second squared.